Section. Introduction. We're going to talk about a fascinating area of machine learning called generative modeling. In recent years, this field has made some incredible strides. One area that's particularly interesting is conditional generation, which is a key component in solving real-world problems like image restoration, super resolution, and creating content with specific styles. However, it's not without its challenges. Conditional generation often requires additional training, data collection, model architecture designs, or extra assumptions about the tasks, which can be costly and limit its applications and potential users. Recently, diffusion models have emerged as a potential solution to these challenges. These models use standard loss functions to guide the sampling process. While they avoid extra training, their reliability can be inconsistent. Sometimes they perform impressively, but other times they struggle to produce realistic images. They also tend to be slow because they rely on extensive sampling time optimization and a large number of diffusion time steps to produce satisfactory samples. Furthermore, we don't fully understand why these methods sometimes succeed and sometimes fail, which makes it hard to design practical implementations for real-life applications. In this paper, we introduce a new framework called Manifold Preserving Guided Diffusion, MPGD. This framework uses pre-trained diffusion models for conditional generation without any extra training, minimal additional computation and sampling time, and it can be applied to a wide range of tasks while maintaining high sample quality. The key idea behind our method is the manifold hypothesis, which suggests that real data doesn't occupy the entire pixel space, but instead lies on a very small underlying manifold. Instead of guiding the diffusion process without constraint, we project the guidance to the manifold throughout the diffusion process. This approach leads to an efficient shortcut for guidance gradients that saves both time and memory and significantly improves the sample quality in low-resource settings. We've developed several new methods for training free guided diffusion generation using this framework. We've also analyzed two practical approaches to manifold projection using pre-trained autoencoders for pixel-space diffusion models. We've found that applying our shortcut to latent diffusion models significantly improves the sample quality and the inference speed. We've also extended the framework to incorporate multi-step optimization algorithms to further improve performance. We've tested our methods against other training free guided diffusion baselines on various conditional generation tasks, including solving noisy linear inverse problems, human face generation with facial recognition model guidance, and text-to-image generation guided by a certain input style. Our experiments show that our methods find a better balance between fidelity and controllability compared to the baseline methods and can achieve up to 3.8 times speedups while maintaining high sample quality. Now, let's dive into the technical details. We're trying to solve the problem of conditional generation by sampling from the posterior distribution, given a certain condition like a text description or an input reference image. We're using pre-trained generative models for the prior distribution and a differentiable loss function to get the posterior. Our goal is to find solutions that don't require extra training, are low cost, can be generalized, and produce high-quality samples. We're using diffusion models, which allow us to sample from a clean data distribution by iteratively using a time-dependent score function for noisy data. In these models, noisy data is obtained by adding Gaussian noise to the scaled clean data. The score function is often parameterized through a denoiser trained with a loss function, so that it estimates the Gaussian noise included in the noisy sample. During the inference time, we can obtain clean data samples by applying the score function iteratively to noisy samples. Section summary. Conditional generation is a crucial task in generative modeling, but it still faces challenges related to cost and generalizability. In this paper, the authors propose a framework called Manifold Preserving Guided Diffusion, MPGD, that uses unconditionally pre-trained diffusion models for conditional generation with minimal additional computation and sampling time. By leveraging the manifold hypothesis and projecting the guidance to the manifold throughout the diffusion process, MPGD achieves high sample quality and generalizability to a broad range of tasks. Section. Training free guided diffusion. Let's delve into the concept of training free guided diffusion. This approach has been explored in several recent studies, including classifier guidance diffusion, DPS, PIGDM, Freedom, and UGD. These methods all share a common principle. They break down a conditional score function into an unconditional score function and a loss-based term. To put it simply, they take a function that depends on certain conditions and split it into two parts. The first part doesn't depend on any conditions, while the second part is based on the difference between the predicted and actual outcomes. This process can be seen as a two-step procedure. First, we start with a noisy sample, which we then clean up using the unconditional diffusion model. Then, we update this cleaned-up sample using the gradient of the loss-based term. If we assume that the noisy log likelihood can be accessed by a time-dependent differentiable function, the second step can be seen as an optimization step. We're essentially trying to minimize the guidance loss near the cleaned-up sample. However, there's a catch. The pre-trained guidance loss function is usually only defined on clean data, not on noisy data. To get around this, we use the clean data estimation from the Tweedy's formula as a point estimation of the true loss term. Many previous methods follow this formulation. For example, DPS deals with inverse problems of the form y equals a, x, plus z, where a is a function of x and z is an additive observation noise. In cases with Gaussian observation noise, it defines the loss as the square of the Euclidean distance between y and a, x. Other methods like LGD, UGD, and Freedom offer more flexibility in designing loss functions, allowing them to handle a variety of tasks. For instance, in the case of face ID-guided generation, Freedom uses a loss that calculates the Euclidean distance between the features obtained by a facial recognition model and the features for the target face image. There have also been efforts to apply pre-trained diffusion models to a variety of tasks without additional training. Building upon these, DPS, DDRM, and DDNM have tackled inverse problems. Several papers, similar to ours, have addressed issues related to manifolds, though their discussions were limited to linear inverse problems. However, there's an issue with the previous formulation. In practice, the data lies in a much lower dimensional space than the ambient space. This is known as the manifold hypothesis. Under this hypothesis, the support of the data distribution of interest lies on a k-dimensional manifold that is embedded in a d-dimensional ambient space, where k is much less than d. Some studies have shown that with the linear subspace manifold hypothesis and Gaussian annulus theorem, at a certain diffusion time step, the noisy data also probabilistically concentrate on a manifold that has a shell-like geometric structure to the original data manifold. However, because the neighborhood resides in the ambient space rather than on the manifold, not all points in the neighborhood are necessarily close to or included in the manifold. This suggests that the results obtained through optimization within the neighborhood may deviate from the manifold and adversely affect the evaluation of the score function in the following steps. Therefore, optimization within the neighborhood cannot guarantee that the final result will correspond to a realistic image. In practice, we observe that methods such as DPS, UGD, and Freedom require detailed fine-tuning of step size scheduling, techniques such as repainting, or a large number of diffusion time steps to ensure that gradient updates don't deteriorate the final results. Section Summary. Many recent papers propose using pre-trained diffusion models for conditional generation tasks by decomposing the conditional score function into an unconditional score function and a loss-based term. The sampling process involves obtaining a denoised sample using the unconditional diffusion model and then updating it using the gradient of the loss term. However, the optimization within the neighborhood of the denoised sample may deviate from the underlying manifold, leading to suboptimal results. Section. Manifold preserving training free guided diffusion. We're going to simplify and explain a section of a paper titled, Manifold Preserving Training Free Guided Diffusion. This paper discusses a new approach to guided diffusion that takes into account the manifold hypothesis. The first part of the paper discusses the objective of this new approach. The authors propose a different way to minimize the objective by considering a different neighborhood than the one used in the original equation. They suggest that since a manifold is a certain type of mathematical space, the neighborhood can be thought of as a subset of the tangent space of the manifold. This tangent space is similar to a subset in a k-dimensional space, where k is much smaller than the dimension of the original space. The authors argue that optimizing on a small neighborhood on the tangent spaces allows us to only make reasonable changes to the samples. They then define a small neighborhood around a point in its tangent space and set a goal to find a point in that neighborhood that best aligns with the given conditions. The paper then discusses how to estimate the tangent spaces of a data manifold using an autoencoder. The authors explain that the information bottleneck in autoencoders naturally incorporates the manifold hypothesis, and a well-trained autoencoder yields latent representations that implicitly capture the local lower dimensional coordinates for the data manifold. However, they note that while most autoencoders are trained on clean data, they need access to the tangent spaces of the noisy samples in the manifold. They then propose a shortcut to perform manifold preserving guidance with access to only the clean data manifold. The authors then present a theorem that if a guidance gradient preserves the manifold for clean data, it also brings a noisy sample on a noisy manifold. They then derive a simplified update rule for manifold preserving guided diffusion that only requires access to the tangent spaces of the clean data manifold. The paper then discusses how to project the guidance onto the manifold using an autoencoder. They first explain the process using a perfect autoencoder, but note that in practice, well-trained imperfect autoencoders also have similar effects for mapping the guidance to the data manifold. In conclusion, the authors propose a new approach to guided diffusion that takes into account the manifold hypothesis and provides a simplified update rule that only requires access to the tangent spaces of the clean data manifold. They also discuss how to project the guidance onto the manifold using an autoencoder and provide evidence that well-trained imperfect autoencoders can also be used for this purpose. Section Summary. The authors propose a framework called Manifold Preserving Training Free Guided Diffusion, MPGD, to address the manifold hypothesis in on-manifold guided diffusion. They introduce an algorithm that only requires access to the tangent spaces of the clean data manifold, and they demonstrate how to project the guidance onto the tangent spaces using a perfect autoencoder. They also show that well-trained imperfect autoencoders, such as VQGANs, can effectively map the guidance to the data manifold. Section. Manipulating the latents. Let's delve into the concept of manipulating the latents. We can maintain the structure of the manifold using a flawless autoencoder in a slightly different way. Instead of adjusting the initial data point, denoted as x_0 vert t, using gradient descent, we tweak the encoded latent variable, z_0 vert t, based on its gradients. After this adjustment, we use the decoder to map it back to the dataspace, giving us a new estimate of x_0 vert t. We call this method MPGDZ. We've detailed this method and compared it with two others in the algorithm section, where we refer to the manifold projection function as g_m. We've also included further analysis in the appendix. Now, let's talk about MPGD with latent diffusion models. Latent diffusion models, LDMs, as proposed by some researchers, is a process that gradually transforms a sample from z_t in a k-dimensional real space to z_0 in a space denoted as z. This z-space is the same as the latent space of a well-trained autoencoder like a VQGAN or VQVAE. Using the same logic, we can manipulate the latents in LDMs using the technique we described earlier. Since LDMs operate on the autoencoder's latent space, the decoded latent guidance is on the tangent spaces of the data manifold. Therefore, assuming a linear manifold, the final sample x_0 is on the manifold M. We call this approach with LDMs as MPGD LDM and provide the details in the algorithm and appendix sections. Next, we discuss multi-step optimization. Our current framework performs a one-step gradient descent on the clean data x_0 vert t for the objective equation. However, we can also use more advanced optimization solvers like the nonlinear conjugate gradient method, and if the manifold remains preserved, we can perform multiple optimization iterations. This could potentially improve both the quality and speed of the process. Although motivated differently, techniques like time traveling or repainting also perform a multi-step optimization to minimize the guidance loss. Specifically, adding noise after each gradient descent step can be seen as stochastic optimization via stochastic gradient Langevin dynamics. We show the results of using both the nonlinear conjugate gradient method and time traveling for Face ID guidance stable diffusion generation in the appendix figure. In the experiments section, we compare the performance of our proposed methods with baselines in 3 experimental settings. For the pixel domain diffusion, we test our methods with a simpler linear inverse problem and a more complex nonlinear problem. For the latent diffusion models, we evaluate our method with 2 conditions at the same time, one included in the pre-trained model setting and the other provided by the loss function, to examine its ability to understand compositional conditions. We also provide further details of the experiments in the appendix. In the Pixel Space Diffusion Models section, we evaluate the performance of our proposed pixel domain methods, i.e., MPGD with O project, MPGDA, and MPGDZ, with two different sets of conditional image generation tasks, solving linear inverse problems and human face generation guided by face recognition loss, which we refer to as Face ID guidance generation. For MPGDA and MPGDZ, we use the pre-trained VQGAN models provided by some researchers. In the Noisy Linear Inverse Problem section, we use noisy super resolution and noisy Gaussian deblurring as the testbed. We choose DPS, LGDMC, and MCG as the baselines. We test each method with two pre-trained diffusion models provided by some researchers, one trained on the FFHQ dataset and another on ImageNet, both with a resolution of 256 by 256 pixels. For super resolution, we downsample ground truth images to 64 by 64 pixels. In the Gaussian deblurring task, we apply a Gaussian blur of size 61 by 61 with kernel intensity 3.0 to original images. Measurements in both tasks have a random noise with a variance of 0.05 squared. We evaluate each task on a set of 1,000 samples. We use the kernel inception distance, KID, to assess the fidelity, learned perceptual image patch similarity, LPIPS, to evaluate the guidance quality, and the inference time to test the efficiency of the methods. All experiments are conducted on a single NVIDIA GeForce RTX 2080 Ti GPU. The generated examples for qualitative comparison are shown in one figure, and the quantitative results for the super resolution task on FFHQ are presented in another figure. All three of our methods significantly outperform the baselines with all metrics tested across a variety of different numbers of DDIM steps, and we can observe manifold projection improves the sample fidelity by a large margin. Section Summary. The section discusses three methods for manipulating the latents in a perfect autoencoder, MPGDZ, MPGD-LDM, and multi-step optimization. MPGDZ modifies the encoded latent variable with gradients instead of updating the dataspace directly. MPGD-LDM manipulates the latents using latent diffusion models, and multi-step optimization employs more sophisticated optimization solvers for multiple iterations. The experiments show that all three methods outperform the baselines in terms of fidelity and sample quality. Section: Face ID Guidance. We've put our proposed techniques to the test on the complex task of generating human face images guided by Face ID. The aim here is to create images of faces that closely resemble reference faces. We've chosen Freedom and LGDMC as our benchmark methods. We've tested all methods using a pre-trained diffusion model for the Celeba HQ dataset, which consists of 256 by 256 pixel images, and used 50 DDIM steps. We've generated 1,000 face images using the Celeba HQ test set as reference images and evaluated the results using KID and Face ID loss on a single NVIDIA GeForce RTX 3090 Ti GPU. The figure shows the generated samples for a visual comparison, and the table provides the quantitative metrics. Our methods show similar or better sample quality with significant speed improvements compared to the benchmarks. We've also observed that our methods can keep the overall geometry generated by DDIM and only alter the semantics relevant to the guidance. This suggests that our method can guide in the tangent spaces of the DDIM samples. We've also evaluated MPGD-LDM, our latent diffusion models, by testing our methods against the same benchmarks as the Pixel Space Face ID experiments with a text-to-image style guided generation task. The aim here is to generate images that match both the text input prompts and the style of the reference images. We've used Stable Diffusion as the pre-trained text-to-image model and applied the guided sampling methods to include a style loss, which is calculated by the Frobenius norm between the gram matrices of the reference images and the generated images. We've randomly created 1,000 conditioning pairs for reference-style images and text prompts, using images from WikiArt and prompts from the Party Prompts dataset. The figure and table show qualitative and quantitative results for this experiment respectively. All the samples are generated on a single NVIDIA A100 GPU with 100 DDIM steps. Our method strikes a balance between following the text prompts, which often instruct the generation to create photorealistic images that don't fit the given style, and following the style guidance, which deviate from the prompts. Notably, because MPGD doesn't need propagation through the diffusion model, our method can provide significant speedup and can be fitted into a 16 GB GPU while all the other methods cannot.